We'll finish up our study into graphs and directed graphs by examining the practical problem of finding the shortest path between two vertices in a graph or digraph that either does or does not have edge or arc weights. Okay, the most popular algorithm by far for solving this problem is called Dijkstra's algorithm, and we're going to learn this algorithm in detail. As I mentioned, we're going to apply Dijkstra's algorithm to an edge-weighted graph. We're going to think of the weights of the edges as conveying a sense of distance between vertices along that edge, okay? And paths we'll think of as having lengths, right? The sum of the edge weights along a path will be the length of the path. Okay, we do this regardless of whether the length really conveys the sense of an actual length or something else. So again, if we had an ordinary graph without edge weights, we could treat that as an edge-weighted graph by simply assuming that each edge had weight 1. Okay, throughout our discussion, S and T are going to denote two particular vertices in the graph, and S is going to be the starting vertex for the path that we're trying to find, and T is going to be the vertex that we're trying to get to. We'll work with undirected graphs, but the same reasoning could easily be adapted to achieve a digraph version of Dijkstra's algorithm. The way Dijkstra's algorithm works is by beginning with S, focusing in on S first, and then steadily discovering vertices that are further and further away from S. Okay, so it pretty much radiates out from S, and if the goal is just to get to the vertex T, then the way this is going to work is that by the time we discover vertex T and process it, we'll talk about what that means, by the time we do that, we can be assured that we will have discovered the shortest path from S to T. Of course, we're going to go forward and look at an example, and hopefully, it'll hit you at that point. But as you proceed, just bear in mind what U dot D means. It means the shortest distance from S to U along paths that have been discovered up until that moment. Okay, that have been considered up until that moment. It's not necessarily the true shortest distance, not until, eventually, but at the moment, while we're visiting V, it's very important to understand that while we're visiting V, V dot D will be the true shortest path from S to V along all possible paths in the graph. Yeah? But U dot D is merely the shortest distance along paths that have been considered so far. It's possible that U dot D will decrease later on in the algorithm, but eventually it will become delta SU. Eventually. Okay, so as I said, if we discover V dot D plus the weight of the edge from V to U is less than U dot D, well, that means that we just found a new shortest path from S to U, so therefore it's time to change U dot D to reflect this fact, and to also change U dot pi to keep track of which vertex, namely V, comes before U. And like I said, for this to work, though, in order to guarantee that at the time when a vertex V is processed, that V dot D really is its true distance from S, in order for that fact to be guaranteed, we have to put vertices in the correct order. Okay? So here's the principle for deciding which vertex to process next. Among all of the discovered vertices, I should say all of the discovered vertices that haven't been visited yet, select a discovered vertex that has the least value of v dot d. Okay? And as long as you follow this simple, you'll process the vertices in the correct order, and everything will work out great. Okay? So you have to choose a discovered vertex to process next. Always choose one that has the least value of v dot d. Human beings can just maybe look at, write this down on paper and so forth. How do we get a machine to do it? How do we get computers to do this? Well, one thing you can do is scan through a list of vertices, and maybe you've maintained this information v dot d inside each vertex object or something like that. That's a possibility. But we might have a graph with an awful lot of vertices. And by now, it should occur to you that if you have a lot of vertices, doing a sequential search is very time-consuming, right? If you had billion vertices and you had to go through and decide which one to process next, you'd be looking for a discovered vertex that has the smallest possible v dot d. Well, you'd have to search sequentially, and that could take an awful lot of time. Okay, so we're going to use a better plan. We're going to use a reverse heap. If you recall, reverse heap is a very nice structure. It's basically the same as a heap, but you keep the smaller numbers at the top instead of the bigger numbers at the top. And we'll use this reverse heap as a priority queue. The one that we pop off the heap, that'll be the vertex that we visit next. So here's the plan. As we discover vertices, every time we discover a vertex, we'll add that vertex to the heap, and we'll use the value of, I say heap, but it's really a reverse heap. We'll add the vertex that's just discovered to the heap, and we'll use its value v dot d will be used as a priority. Whenever it's time to process a new vertex, just extract a vertex from the reverse heap. The entire algorithm can then be described as follows. Begin with S as the only discovered vertex and all the other vertices as undiscovered. Push S onto the reverse heap. Let me point out that we earlier mentioned that S dot D is 0. So it should be mentioned here too. It's not. We initialize S dot D to 0. Initialize all of the other vertices V. We initialize V dot D to infinity. Okay, and follow this. Do the following in a repeated fashion until T is extracted from the reverse heap, or until the reverse heap is empty. If we extract T from the reverse heap, we'll have arrived at T, and we'll be ready to process T, and we'll actually know that T dot D will actually be the true distance from S to T at that point, and it'll be time to quit. Okay? If we never extract T, but we wind up with an empty heap, then we will have visited all the vertices that are as possible to reach S. Okay? All the vertices that are in the same connected component as S will have been processed, and T will not have been among them, so we can conclude that T is not reachable. It's not in the same connected component. All right, anyway, here's what we do in a loop. The vertex at the top of the heap, well, it's actually reverse heap, but I'm gonna say heap. Okay, the vertex at the top of the heap is the vertex that we want to process next. Okay, so that's all. We just look and see which vertex is at the top of the heap, and we process that vertex. When we're done processing that vertex should be removed from the heap. I think I say so further down, but anyway, that's true. We'll remove the vertex V from the top of the heap after we've finished processing it. We process V as was discussed earlier, meaning that we'll examine each of the neighbors U of V, and for each U that's already processed, we'll ignore that. But for every other neighbor U, we'll have to consider changing the value of U dot little d. U dot little d is the current known distance from S to U, right? U dot little d, current known distance from S to little u. It might be infinity. If it's infinity, that means that this vertex U was undiscovered and now has just become discovered, right? If a neighbor has U dot little d equals infinity, then we'll be seeing that vertex U for the first time. We'll be discovering it, and therefore we will definitely change U dot d, and we'll put that new discovered vertex U onto the heap. Okay, that's important. Every newly discovered vertex U has to be put onto the heap using U dot d as its priority, right? Using the new value of U dot d. The value of U dot d was infinity, but we changed it to a finite number, and then we put it onto the heap using that U dot d as the priority. Okay? But if we encounter a neighbor U of V that was previously discovered, well, that means that it's already in the heap. It's already in the heap, and it already has some finite value for U dot d, and we might or might not change that value of U dot d, as we discussed earlier. If V dot plus the weight of the edge from V to U is less than U dot d, then we have to change U dot d. Okay? And that raises actually a little technical problem, because we've already put that vertex U into the heap using U dot d as its priority, but now if we change U dot d, then we will have to change the priority of the node in the heap. Okay? That's not a big deal. It's actually fairly straightforward to change the priority of some node in a heap, and if you do so, it might entail doing some heapifying up or some heapifying down to restore the heapness, the heap property of the heap. Okay, but anyway, that's what we do with neighbors U that were already previously discovered. We consider the possibility that we might have to change the value of U dot d, and if we do so, then we have to fix things up in the heap a little bit. So we keep doing that in a loop, repeatedly processing vertices and adding to the heap and removing the top node after we visited a vertex. We remove it from the top of the heap, right? Now, either we did or didn't remove T. Assuming that we're trying to get to specific target vertex T, then either we did or we did not remove T, right? If we had not removed T and we kept looping until the heap was empty, then, as I said before, then there's no way you can get from S to T. There is no path from S to T. Okay? But on the other hand, if we did manage to extract T, at the exact moment, well, actually, at the moment when we decided to start processing T, because T was at the top of the heap, as soon as that happened, at that moment it's guaranteed that T dot D is equal to delta ST. Okay, as we discussed before. As soon as we arrive at the point where we would start to process T, it's guaranteed that T dot D is the correct distance from S to T. Okay, so maybe we could just stop at that point. All right. If we do find T, and if we think about it a little bit, not only will we have the distance from S to T, namely T dot D will be the actual distance from S to T, but in fact, we'll have enough information to reconstruct the shortest path to get from S to T. And here's why. Consider this sequence of vertices. Starting with T, consider T dot pi. Well, T dot pi is another vertex, right? And then consider T dot pi dot pi. So that would be the dot pi of T dot pi. And then consider T dot pi dot pi dot pi. And I claim if you continue this, eventually this process has to take you to S. Okay? This sequence beginning with S will terminate, this sequence beginning with T will eventually terminate at S. And this sequence will actually be a path from T to S, right? Because we know there's an edge that connects T to T dot pi. T dot pi is a vertex that comes just before T along a shortest path from S to T. Okay, that pretty much was by construction, that's the case. And then T dot pi, well, that has to be a vertex that comes just before T dot pi along a shortest path that connects S to T dot pi, and so on and so forth. So if you think about this for a second, not only is this path that goes from T to S, it's actually a shortest path that goes from T to S. So now if you simply reverse that path, you get a shortest path from S to T.